Hey guys, how you doing? It's Coach Scott here on Coach Scott's Chemistry. We're going to, let's do that. All right. So what we're going to be doing is we're going to be working this problem sheet like I gave you. What we're doing here is you got to read the question, and what we're talking about is phase change. And this is a physical process where energy is going into the different phase that you're in, and you're attacking those forces that are holding those particles together, right? We call those intermolecular forces. So if you look right here, and I got real fancy, I've got my little snag it thing here. Let's go up here and choose a pen. Let's use that one. First of all, I'm going to draw a phase change diagram so I can understand what's going on. Let's draw it up here. So I've got an a y-axis. Oh, there we go. Y-axis. I got an x-axis. This is going to be in temperature. All right. And this is going to be energy. Now here we're adding energy into the system. Okay. And let's see what we got. How much energy is required to convert 54 grams or 3 moles of ice? So we're talking about solid water at minus 15 degrees C to steam at a temperature of 105 degrees C. Now at first blush, we could say, okay, we can just get the delta T, 105 minus negative 15 Celsius, and then I can use the mass and I can use specific heat. But we really can't do it because if you look right here, the specific heat capacity of ice, the specific heat capacity of water, and the specific heat capacity of steam, each of those different phases is going to require a different amount of energy to attack those forces that are holding those molecules together. And that's why we have this phase change diagram. Let's see where I'm at here. So let's say this is minus 15. Okay. I'm going to go up. When I reach 0, we know that's the melting point. So I'm going to plateau off with a slope of 0. Then after all the material has been melted and it's no longer ice, I'm going to start going up again. I've got a slight increase going on until I reach 100 degrees Celsius. And then what happens with water, it starts to boil. After all that water, the 54 grams or 3 moles is boiled, I'm going to continue to go up because now that steam starts to get heat and it gets excited. So we're going to be measuring, we'll say that's the minus or the 105. Change the color here. Let's go to orange. All right. So we'll say that's minus 105 or 105. So that's 105 degrees C. Okay. We know that this area right here is 100. So that's 5 degrees. It went from 100 up to 105. There's 100 degrees. All right. That's 100, or excuse me, that's at 100 degrees. Now again, what's going on there? We're not changing temperature, but we're throwing energy into it. You can see the energy is increasing on the x-axis. We are adding energy right here. All right. We're adding energy and the temperature is changing. So again, like I told some of y'all earlier, we've really got to break this down into 5 different phases. All right. And we've got to determine the amount of energy at each of those phases in order to get a correct sum of the energy required for what we're doing. So we can call this Q1. And what's going on? We're going from minus 15C to 0C. So that's our first change, right? Then we're converting this material. That's where the phase change really happened. So that's really Q2. Now after that 54 grams of water is converted, all right, it's melted from a solid to a liquid, then we have another phase where we're throwing energy into it. This we call Q3. After we've increased that to 100 degrees Celsius, Okay, this is now boiling away. We'll call that Q4. And this area we call Q5. Now we've got three different formulas we're going to use. The first one, my favorite, Q equals mass times specific gravity times delta T, or as I like to call it, QMCAT. Now this we can only use whenever there's a change in temperature. So those areas are going to be right here. So you're right here at Q1. All right, here in this area right here, where are we at? There we are. All right, in Q3, we can use QMCAT. And then this area, this little area, right, where are we at? Right here, where we go from 100 to 105 F or C. So we can use QMCAT. Now if you look over here, each of these different areas have a different specific heat. So when we're ice, the specific heat is 205 joules per gram. When we're water, the specific heat is 4.18. And when we're steam, the specific heat, okay, is 2.08. So each of these have a different C. So we've got to make sure we use the one for ice in this area here. We got to make sure we use this term for water when we're going up like this because it's liquid. And we got to make sure we do the right one for the steam, which is right here. So the Q2 and the Q4 area, then we've got to use a whole different little formula entirely. Let's go here. Let's see what we got here. I think this is one of those, so we'll go here. There we're going to use fusion, all right, which the formula is this. The heat of fusion is equal, and this is called the molar heat of fusion, a constant, the delta H of F fusion times the number of moles. Again, we're not going to worry about what a mole is right now. In about 2 months we will. So there we know we've got 3 moles. And it gives us the heat of fusion for H2O, which is 6.02. Now in this area here, we're vaporizing, all right? So we're going to use the molar heat of vaporization. So we can get Q, let's call the heat Q, of vaporization, vape, not vaping, vaporization, is the delta H, which is a constant for each substance of vape, times the number of moles, which is the amount of something. Now, what's important in my mind that you understand is that you understand this diagram, that you're going to have a different amount of heat required due to the specific heat of ice. All right, you're going to have a different Q here when we're melting the ice, and you're going to have a different Q here again because of the heat capacity of the liquid water, 4.18 joules per gram per degree K or C, and a different amount of energy because of the vaporization factor. Okay. Then of course here we're controlled by QMCAT. Now how I would solve this, like I did for some of you guys, I'd break that down and I'd do Q1, because if you think about it, Q1, if you figure that out, you add that to Q2, and you add that to Q3, and you add that to Q4, and you add that to Q5, you will get the total amount of energy that's required to melt and boil 54 grams or 3 moles of ice, of water, all right, in each of the phases. If you understand this concept, you've got it, okay? Now, we'll be doing the math for this problem in another video, but this is a quick summary of what a heat or a phase change we're going through, okay? And that's all I'm really worried about right now. I'm worried about you understanding the phase change of what's going on in this diagram, okay? We're heating the material that's starting to get enough heat to break those forces that are holding the molecules together. You're melting it. Again, that's taking a different amount of heat. You're raising the temperature or by adding heat into it until it starts to boil, which it does right here. And then the steam or the gas vapor that's formed from the boiling is then again heated with a different amount of heat. You've got to add all that energy up to get the total heat. All right. Hopefully that helps you guys out a little bit. I'll do another one where I'll do the math to this, and I think that might help you guys out a little bit more. All right. As always, have a good evening. It's Coach Scott signing off. See you guys tomorrow.